Hey guys, it's me again. So hey, today we're gonna read another textbook, which is a textbook about information theory and neural network. So for this time, I'm doing two courses. One course is Mastery 411, which is information theory course, and another course is 9444, which is about neural network. And then what happened is, although I have done 2111, which is a multiple variable calculus course at the start of this year, but I forget all of my knowledge. And also, I haven't done too much with statistics. I think I've touched a little bit in my first year entry course, and yeah, I also forget most about binomial distribution, which is what I've learned from high school. So I felt it's necessary for me to read some textbook beside of doing a lecture. I mean, read just watching the lecture plus the questions because I felt like I couldn't do those questions by myself. I don't know, I just couldn't do it. I can do some easier one, but for some harder ones that require a bit of binomial distribution, then I'm unable to do it, and it's pretty bad, right? So and yeah, let's just read the textbook. So what I found about this textbook is I felt like it's best for me to communicate with myself again, once again, emphasize that. And yeah, when reading this textbook, what I feel is like there are some maths that I don't understand, and it's pretty bad to be honest. Which why I couldn't understand. I just yeah, for last year I haven't done too much serious study about maths, and my math skill just drifted away, I guess. So but let's get into it. This textbook is fun. I have read. Actually, it's not easy to me. So what happened to me is like I get around sleepy while reading the textbook. What I mean by that is like so today morning my routine is like today's morning try to do some study, then did about 30 minutes of math, and then fall asleep, and then would have a shower, have a lunch, and then trying to do some study, but then don't know what to start. So I downloaded textbook, right? And then I print some chapter of this textbook and want to study, and then I study for 30 minutes, and then I felt so tired, and then falling asleep. And when I wake up, I try to concentrate myself to do some study, and then I fall asleep again. And that's how it work. And this is my like first time trying to do some serious study today, and it's already 4 p.m. It's terrible. And also tomorrow there will be another tragic event, which I will. So like I do make trouble in this course. To be honest, I can understand lecture for now, I guess, but I couldn't understand how he proved it. But to understand how he proved it, I need to go back to restudy all the work I have been missing for the last year, which is ton of work, which I couldn't do. It's just impossible. And if I want to keep doing my degree, I have to keep like you know it's just very hard for me to keep up with stuff. It's already happened, so already like couldn't even do the second level seven, level two math course, and yeah, also a funny story. So I got a friend, right, and he or she is very good at math, but I couldn't ask for help because some reason I just couldn't ask for her help, which makes me feel stressed, right? It's very normal though. It's like the math is pretty hard, so when I read it, I get stressed. So okay, let's just keep reading this textbook. So what I'm in trouble with is here. So I couldn't understand what this means. So well, by the Bios theorem, yeah, maybe a good idea would be like just simply search it up. It wouldn't show in this screen because in this screen I'll just show in the textbook. If anyone's watching, that's like my explanation. So basically what happens is, so probability of B happens and A happens is equal to A happen and B happen. times A happen divided by B happen. Whew. 现在是this just I mean this is just applying this formula, so this doesn't matter. Okay, so R is represented by received bits. And what's S? S is a single bit. So given the 3-bit happens, probability of S happens is equal to, given S happens, and 3-bit happens, times by S happen, divided by 3-bit happens. And then we can spell out the posterior probability of two alternatives, just like S equal to 1, then it equal to that, given the S equal to 1 happen and probability S equal to 1, this 3-bit happen, and also divided by this 3-bit happen. The posterior probability determined by the two factors, the parallel probability PS and data-dependent term P, R1, R2, R3, given by S is a conditional probability, which is called the likelihood of S. The normalization constant needed to compute it when finding the optimal decoding decision, which is to guess S equal to 0 if P S equal to 0 are greater than P. Yeah, that's right. So what's P? Wait, is P a probability? Oh, we should have this go up. Nope. Too far. Okay, I'm confused here. So if no, I don't understand this paragraph. You know what? I agree with this. Then maximizing the posterior probability. Well, let me just search this word. I don't really understand what's posterior probability. Is that like a certain word? It's type of conditional probability that resulting from updating the parallel probability with information summarized. Okay. I sort of understand. Okay, this posterior probability determined by two factors, the parallel probability PS and that dependent term actually makes sense. Oh wait, what? What is this? I saw like this should be just this. It's called that dependent term. So this means that given the S is happened, then what's the probability of this, which is called likelihood of S. The normalization constant needed to compute when finding the optimal decoding decision, which is to guess. To find the P S equal to 0, given the R happens S equal to 0, we must make assumption about parallel probability of two hypotheses, S equal to 0 and S equal to 1. We must make assumption about the probability of R given S. We assume the parallel probability are equal. Okay, parallel probability refers to before the event happen, S is 0 or S equal to 1, and we assume this is equal. Then maximizing the posterior probability, which is posterior probability is equivalent to maximizing the likelihood. This sentence I don't understand. Then maximizing the posterior probability is equivalent to maximizing the likelihood. And we assume the channel is a binary symmetry channel whose noise level f is smaller than 0.5. Thus the likelihood is oh, you know just one thing, right? So when I'm talking to myself, it makes me less sleepy, and I feel better. So I still don't understand the math. That's a problem. So by myself, I couldn't understand math. I have to ask someone to help me. But yeah, ask that person is no longer an option for me. Just not. So I literally got no one to ask, right? So actually wait, do I? No. Forget about it. Yeah, the problem is like, okay, just skip this part. So I don't have to understand the math to, I kind of understand how it works, but I don't understand the math, but that's kind of like the problem if you don't understand math. We now apply the majority vote decoder and receive factor of figure 1.8, which it is. Then the decode rule gives the wrong answer as shown. Yeah, so if unlucky, then 10% transmitting most useful code. The error probability is dominated by the probability that 2-bit in a block, which I understand. I don't understand the math. I just don't understand the math, how the math works. I need a bit of probability before it, but crap. Actually, it's only need binomial distribution, but I also don't know too much about binomial distribution either. That's the problem. Graph 8. Figure error probability of P versus the rate of repetition code of a binary symmetry channel with f equal to 0.1. The right-hand figure shows the PB on a logarithmic scale. I'm sorry about what's rate. Repetition code R3 are therefore reduce the probability of error as desired. Okay, so I don't answer rate. What's rate supposed to mean? Oh, I see. So rate means like the rate of information that being passed through. Because if the repetition code is 3, then it means only 1/3 of information is raw information, and 2/3 is redundant. And then this graph shows that okay, I think I can understand it. Repetition of R3 therefore reduce probability of error as itself. Yet we have lost something. Our rate of information transfer has fallen by the factor of 3. So if we use the repetition code to communicate data over a telephone line, it will reduce error frequency, but it will also reduce our communication rate. We'll have to pay 3 times more money for the phone call. Similarly, we would need 3 of original noisy gigabyte disk in order to create a 1 GB disk with PB equal to 0.03. Can push the error probability lower and the value required for the sellable disk to 10 to the power negative 15. We will achieve lower probability by repetition code with more repetition. Shows that probability of error and with n repetition is that for odd n. Okay, I think I should try to solve this problem if I could, right? I think that this is like a tutorial problem for also my course. Like I have to, let me just quickly check that if so that's awesome, right? I'm also solving a problem for, not too sure. Lecture 2 we have talking about the two things. One thing is called the 8-byte error correction code. I'm not sure if it's called that. It's just I'm sure it's called like that. Anyway, forget about it. And binary repetition code. Cool. So we were told about binary repetition code, but hey, where is my sorry, I'm trying to find the question sheet that we were given. I think I found it. And is that like one of the questions? Nope, I don't think so. I don't have canon code. Forget about it, I will try to solve it by myself, and I think there's an answer in the back, so if I couldn't solve it, then I will just check out the answer and write it down. Crap, I couldn't solve this problem. How I solve it, right? Let's be realistic. So the question is, let me just show the question. The question I'm trying to solve is this problem. So the probability of error in Rn with repetition of n repetition is that, so it's PB equal to sum of n. Oh wait, I think show that. I don't have to show that, right? It's just what it is. Oh, but we can argue with that, right? So, so suppose there is an error. I think it's also on my lecture slide, but anyway, suppose that there is an error for a bit that unable to be detected. It is strictly greater than, just greater than, then it is greater than n plus 1 divided by 2. Yeah, n plus 1 divided by 2. Hence, the probability is above. And so also I have a look at slide. I think slide says something very similar to what I just been claimed. No, it doesn't make me feel better. Assuming that f equal to 0.1, what is the term in this sum is the biggest? How much bigger is than the second sum term? So it is when n equal to n plus 1 divided by 2, and the second biggest is second biggest should be n equal to n plus 1 divided by 2 plus 1. And how big is should be divided by 10. I mean, just this is just roughly speaking. Roughly speaking, it should be in that way. And then you see, using the Stirling approximation to approximate the n chosen n in a largest term, and find approximately the probability of error of repetition code with n repetition. What the hell is that? I'm not sure if I printed that. Crap. I never heard of this. Okay, so we see. No, I don't search it up, so it's really something that I don't know, right? And it's very normal. I don't know too much. Like, I didn't pay attention for this thing, so it's very normal for me to don't understand a thing. And it is called the Stirling approximation. Cool. And in mathematics, Stirling approximation is an approximation for factorial and oh, okay. So, okay, so n chosen n is equal to n factorial divided by n factorial times n minus n factorial. Saying like this, bigger and smaller n, so it's not all same n, which will be weird, right? And how do you apply it? This is funny because I don't know how to apply it. Okay, forget about it. Assuming f equals 0.1, and how many repetitions are required to get the probability of error down to 10 power of negative 15? Yeah, whatever, I'm going to check out the solution. Wait, don't tell me there's no solution. So my heart will break. We're going to solution ASAP. Come on, solution. Basic solution. This is exercise 1.3. Great, I think there is solution. Oh, there's no solution. Okay, the probability of error by repetition code is dominated by the probability that n divided by 2 be a flipped. I agree. Binary entropy function, what the heck is that? Okay, can be approximated by the binary entropy function. Okay, it is a thing. Right. Information system, the entropy function. I forgot about it. What the fuck? I couldn't even do this first few exercises. It's so dumb. No, but I don't understand. I need to understand just a function. Come on, I feel so confused. A P2, I don't see that formula. Yeah, forget about it. It's so dumb. Well, apparently you use some stirring approximation to get formula and then you substitute in. So build a single gigabyte disk with the core reliability of noisy gigabyte drive with F equal to 0.1. We will need 60 of noisy disk drives, and the trade-off between error probability and rate of repetition code is shown in 1.12. Correct? I don't. Do they surely know this for this textbook? If so, I need to switch textbook ASAP. Damn. Also, the lecture is not very useful, to be honest. At least that's how I felt. Come on. Start approximation. Okay, how about binary repetition code? Some useful resource for this ornament. I found a cool to cover this stuff. I need a lecture to do with me because I just feel lost quickly. Mainly because I'm stuck at this. I deserve this. I haven't studied enough. Cambridge course. So from my understanding, the professor got a course for this. Neural network. The problem is it's really old lecture. Okay, I see, I understand. So the postal it means like given this sequence, what likelihood that this sequence represent? Although I still don't understand the math, to be honest. I just be honest. Lisa. Okay, my decision to give up this sort here to understand training approximation. I'm not sure, but have I seen that in CLRS textbook? I might. Anyway, it's just a formula that I don't understand. So let's focus on broad code. Hamming code, you would like to communicate with tiny probability of error and at a substantial rate. Can we improve on repetition code? What if we add redundancy of block of data instead of encoding one bit at a time? We now study a simple block code. A block code is rule for converting a sequence of a source bit S of length k, say, into a transmitting sequence T of length n bits. To add redundancy, we make n greater than k. In linear block code, the extra n minus k bits are linear functions to the original k bit. These extra bits are called parity checking bits. For example, Hamming code with transmitting 7n equal to 7 bit for LVK equal to 4 4 source bit. The encoding operation for the code shown pictorially in 1.13. We arrange 7 transmitted bits in a 3 intersecting circle. The first 4 transmitting bits are set equal to the 4 source bits. The parity checking bits are set so that the parity within each circle is even. Well, from my understanding, just like the 4. I mean, I don't understand why you use the picture. The picture doesn't make any sense, but I can understand what it means. What the delivering is saying that each bit represented the first 4 to make it even. So this bit will make this 4 even, and oops. Okay. A block code is a rule for converting sequence of bits as length k into transmitting sequence t of length n bit. N equal to 7 and k equal to 4. Okay, so this is a code long transfer, and then it will be this 4, and then it want to make it even. So I'll call this 2 to be 1. I cannot understand what's going on, so this will be T5 should be 0. Because okay, so 4 is like 1, then to make it okay, I think I got it. Hamming code, great. And because Hamming code is a linear code, it can be written compatibly with a term of matrix as follows. The transmitting code word T is obtained by source sequence by a linear operation. When we invent a more complex encoder S2T, the task of decoding of receiving vector R becomes less straightforward. Remembering any of the bits may have been flipped, including the penalty bit. If you assume the channel is a binary symmetric channel and that all source vectors are equitable, the optimal decoder identifies the source vector whose encoding defers to the receiving interference bit. We could solve the coding problem by measuring how far R is from each of 16 cohorts, then pick the closest. Is there a more efficient way to finding the most probable source vector? Syndrome decoding by the Hamming code. Hamming code is a pictorial solution to the coding problem based on the coding picture. The first example, let's assume the transmission was at t equal to 10000101 and the noise flip of second bit and then receive. We write the receive vector into 3 circles shown in 1.15 and look for each. The circle whose penalty is not even and shown dashed line. Okay, I see. So if 2 circles went wrong, no circle went wrong, then no check. If 2 circles went wrong, have to correct the middle one. Okay, so I know a bit of pro, but once again, I don't know how to prove it. Some, yeah, so some, yeah, so some Hamming coda is useful, particularly. I think that's the.